All right, so for our second problem, we have another polynomial, and for this particular polynomial, the first thing that we want to find out is what its derivative is, and then find the slope of this particular function at x equals 3, and then find the equation of tangent line, and then the values where it has a horizontal tangent line, okay? So to start off here, we know that if we find the derivative of this would just end up being 4x cubed minus 16x plus 0. And of course, 0 is the derivative for any constant. So we could stop here. I'm going to go a step further and factor it out because it may help me out in some of these other questions that I have to answer here. So I can factor out a 4x out of both terms. And that will leave me with this. And of course, x squared minus 4 factors out to x minus 2, x plus 2, okay? Not saying that you have to do this, but this may come in handy later. So next, we want to find out what is the slope of the function at x equals 3. And so here what it's really asking is, what is the instantaneous rate of change? Or what is the slope of the tangent line of this function at x equals 3? So essentially what this is asking for is f prime evaluated at 3. Okay? So what we can do here is just take what we found evaluated at 3 and get our answer here. So therefore f prime of 3, if we can plug in everything here, and actually makes it quite simple to do. Okay, so we've done that. Of course, this is 12, that's 1, that's 5. So here the result is 60. So what this means is f prime of 3, or the instantaneous rate of change, or the slope of the tangent line of the function f of x at x equals 3 is going to be 60. And so now that we have that, we can find the equation of the tangent line. So in order to do that, of course, we know with a line we need to have a slope and a point, or 2 points. And so in this case, we already have a slope. We just need to know what the point is. And so to find out what the point is, of course, we'll just plug in 3 into our original function. Okay? So here we'll come over here and do part C. We'll come down here and do part C. So f of 3 will be 3 raised to the 4th power times 8 times 3 to the 2nd plus 9. So we have 81. 3 squared is 9. And of course, 8 times 9 is 72 plus 9. 81 plus 9 is 90. And of course, this gives us a difference of 18. So therefore, using the point slope form of an equation of a line, we can plug in our slope and plug in our point now. Be 318, x1, y1. So y1 is 18, slope is 60, x1 is 3. And so then from this point, you can either leave it like this, or if you wanted to answer it in slope-intercept form, we would manipulate. So we'll add 18 to both sides. After doing this first, add 18, and then 180 minus 18 would be minus 162. So this would be our equation of a line here. okay? So to recap before we finish up the last part, we see that if we take the derivative of the function, it's going to be 4x cubed minus 16x, which we also wrote in this form here. We saw that the slope of f of x at x equals 3 is just 60. So I'm going to rewrite all of this. And just say that that's 60. The equation of the tangent line at x equals 3. Of course, we've done this and found the answer to that. So I'll erase all this work. Equation, tangent line. Okay. And so now the last question that we were asked were the values of x where f of x had slopes that were horizontal. Or some variation of the theme of that. Of course, from last problem, we know we have a horizontal tangent line. That's where the slopes of the tangent lines are 0, where you either have a peak or a dip. And so here for this one, we already have the derivative and we have it in our factored form here. So it turns out that this does help us out some. So we want to find out when the derivative is 0. And of course, having this already written out in factored form makes it real easy to do. So wherever these, whatever values of x here, make our whole equation 0. And of course here, that means that this is 0, or this is 0, or this is 0. So x is equal to 0, x is equal to 2, or x is equal to negative 2. So at these places here, this is where the graph of our function here will either have a peak or a dip, okay? All right, and so this concludes the application portion of the differentiation rules series.